All right, so today we're doing the two parts of the fundamental theorem of calculus. Why is it fundamental? Because it relates how integrals work with derivatives. The two are actually related to one another. In the early beginning stages of calculus, don't ask me when it was, I don't know, but in the time of Newton or Leibniz, people were working on calculus, actually before them even, and people were working on integral calculus and people were working on differential calculus, and no one had realized yet that the two were related to each other. Eventually, someone smart figured it out. Again, I don't know who. My math history is sorely lacking. So, the first part of the fundamental theorem of calculus says this. If you have a continuous function f on a closed interval from a to b, then the function capital F of x, which is defined as the integral from a to x of f of t dt, is differentiable on the interval from a to b, and the derivative of capital F of x, which is the derivative of this integral defined function, is just f of x. Basically, what they're explaining to you here is that the derivative with respect to x and the integral going to x undo one another. They are, in effect, inverses of each other. All right, so it's actually a pretty easy idea, and it's not terribly surprising because we've been doing antiderivatives when we've been doing integral problems. But it is pretty important. Here's one way that we can use it, and that is these derivatives of these integral defined functions. I do want to point out here that you're like, why suddenly is this t and dt? Because they didn't want it to use the same variable that we've already used here. We try not to use the same variable for two different things. Also notice it doesn't matter what a is. A can be any constant. It can be 0, it can be 74. It really doesn't make any difference. So if I have a problem like this, I want the derivative with respect to x of the integral from negative pi to x. Again, this is just a constant. Doesn't matter what the constant is. All I'm going to do is take the integrand at x. It's cosine of x. Done. There is no more work that needs to be done to that. It's the derivative of the integral. The derivative with respect to x and the integral going to x simply undo one another. Now, yes? Oh, why did I give you the notes? I'm very sorry. Now, could you do this a longer way? Yes, you could. Do not bother writing this down, but let me show you. So, what I'm going to do is actually evaluate this integral like it was a definite integral. It's not because this is a variable, but I'm going to do it anyway. So what would be an antiderivative of cosine of t? Sine of t. So I'm going to take the derivative of sine of t evaluated at x minus sine of t evaluated at negative pi. So that would be sine of x minus sine of negative pi. Right? What's the derivative of sine of x? It's just cosine of x. And sine of negative pi, even if you don't know what it is, it's not important because sine of pi is some constant, right? It has some constant value. It's not a function. When I take the derivative of something that's constant, what do I get? 0. Done. So could you go through this? Yes, you could. Is it worth your time? No, it's not. Okay, use the fundamental theorem part 1, and it's a lot faster. So let's take a look at this one. Again, the derivative with respect to x. I've got a function going to x. Those two have to match. Doesn't matter what this constant is. It can be any constant. This is going to be 1 over 1 plus, I'll replace the t with x, and it's 1 over 1 plus x squared. That's all there is to it. Now, let's do some that are a little more interesting. For this one, how is this next example different than the first two? Yeah, it's no longer just x, it's x squared. Think of this like it was a composite function. In fact, if you want to put that in parentheses so you think about it like a composite function, it's not a bad idea. When you take the derivative of a composite function, what is it that you have to use? Got to use the chain rule. So this is going to be the derivative like normal, leaving the inside part alone, so that'll be sine of x squared, times the derivative of the inside part, which is 2x. And most of the time, if this is a multiple choice question, they're going to write it with a 2x in front, so they don't have to write the parentheses. Is it greatly simpler? No. Does it matter? No. If you leave it like this first one, it's just fine. Okay, just know that if it's a multiple choice question, they're not going to leave it like that. All right, what's different about this one? Yeah, well, I don't want it that way, do I? What happens if I switch those? Yeah, so this is just the derivative with respect to x of the opposite of the integral from 7 to x of 4t cosine t dt. By the way, on the ones before, we could find an antiderivative for all of those. For this one, can't do it. In fact, in this class, you guys won't learn enough to do this. BC has to learn how to do antiderivatives like this, but you guys don't. Okay? But you won't learn how to find antiderivatives of that, and you don't need it. We're just going to use the fundamental theorem. Since now this and this match, I'll be like, okay, so this is going to be negative 4x cosine x. All right, this last one, going to need a little room for it. How is this one different? Pardon? Yeah, there's two different functions. There's no constant. Okay, well, here's what we can do then. And we won't do this except on this one example, and then you're like, oh, I can skip over all that. I'm going to rewrite this as the integral from 3x to, oh, pick your favorite constant. So boring. 1 over 2 plus e to the t dt plus, what would I have to write here? I'm sorry? I'm having trouble hearing the first part. 0. Yeah. 0 to x to the 4th of 1 over 2 plus e to the t dt. And now we can do exactly the same thing we did on the last problem. Notice we wanted the constant to be on bottom. We're like, okay, I can do that. This will be the derivative with respect to x of the opposite of the integral from 0 to 3x of 1 over 2 plus e to the t dt plus the integral from 0 to x to the fourth of 1 over 2 plus e to the t dt. In both cases, I'm going to have to use what? Chain rule, because this is not just x. So this is going to be negative 1 over 2 plus, we'll replace the t with 3x, so that's e to the 3x times 3 plus 1 over 2 plus e to the x to the fourth times the derivative of x to the fourth, which is 4x cubed. All right, I'm going to do two things at once. I'm going to multiply these together so that it's a single fraction, and I'm going to write the positive one first. This will be 4x cubed over 2 plus e to the x to the fourth minus 3 over 2 plus e to the 3x. Did the part where we broke it at 0 really affect anything? No, we could have broken it anywhere. And in fact, if we just ignore the bottom for just a second, we would get this when we took the derivative, correct? We would get this first term. And if we ignored the top and said it was 3x to some constant, we would get this. So you don't have to go through all that. You can go straight to the answer. Okay? It'll just be as if we had a constant on the bottom and went to the x to the fourth and took that derivative minus the other way around. Okay? Clear as mud? Okay. So here's the second part of the fundamental theorem of calculus. Which state is calling me now? Oh, it would be my daughter. Yeah, she can wait. So, if f is continuous on the closed interval from a to b, again, same thing we had before, and if capital F is any antiderivative of f on the closed interval from a to b, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. Okay, we've already done this. It's what you were doing to evaluate things, our definite integrals, by finding an antiderivative. Again, as I did yesterday, I think sometimes it's better to think of it as the integral from a to b of g prime of x dx is equal to g of b minus g of a. Okay, questions about that? Okay, so then we can do things like this. Evaluate the integral from -1 to 3 of x cubed plus 1 dx without a calculator. Up till now, we didn't really do that so much, but we kind of did this on last night's assignment. I just need to find an antiderivative. What is an antiderivative of x cubed? Perfect. 1/4 x to the 4th. Plus, what's an antiderivative of 1? X. And if you want to put plus 37 at the end of this, go for it. But you could put plus any constant. It doesn't make any difference. It can be any antiderivative. What's going to happen is they're going to subtract out. The way that we write this is we put those in square brackets and say we're going to evaluate that from -1 to 3. So that'll be 1/4 of 3 to the 4th plus 3 minus 1/4 of -1 to the 4th plus -1. Let's see, 3 to the 4th, that's 81/4 plus 3 minus, that's going to be a positive 1/4, and it's minus a -1, so it's going to be plus 1. I think I told you guys this earlier. I always, with ugly ones like this, I'd add the whole numbers together. That's 4. And then I combine the fractions. In this case, it works out really nicely because it's 81/4 minus 1/4 is 80/4, which is 20. So that ends up just being 24.
It would be 22 because it's plus 1.
What?
Because it's plus, like, the step above plus -1. Wouldn't it be -1?
It's minus -1.
Right.
You got to distribute this negative sign. And that's an easy place to make a mistake, unfortunately. It may be helpful if you tend to make that particular mistake to add another step in here and go minus 1/4 minus 1 and then distribute the negative sign. I just have done this so long that I tend to skip over that step.
Right.
But it's not a bad idea to do that. Okay? All right. All right. This problem, there'll be one like this on the test. I think there's one like this on the quiz as well. And it gives students fits. And it's really not super hard, but it's not as easy as some students try to make it. Okay? Remember that the integral of a function over an interval gives us positive for areas that are above the axis and negative for areas that are below the axis. Everybody remember that? All right. Here it just says find the area. Area is all positive. There is no such thing as negative area. So we can't just do the integral of 4 minus x squared from -1 to 3. It won't work out. That will give us some sort of displacement area or something, but it's not just area. So we need to draw a quick sketch of this. Let's see. 4 minus x squared from -1 to 3. Well, that's going to be an upside down parabola with its vertex at 4. Let's see, at -1, that's going to be 3. So that's right about there. And then notice that this is going to go through the x-axis at 2 and continue going until we get down here to 3. If we do the integral from -1 to 3, what it's going to do is it's going to count all this part as positive and all this part is negative, so it's not going to give you the area. We want the total area between these two. So what we'll do is we'll do the integral from -1 to 2 of 4 minus x squared dx minus the integral from 2 to 3 of 4 minus x squared dx. So again, we have to think of an antiderivative. An antiderivative for that, the simplest one would be 4x minus 1/3 x cubed. So we'll evaluate that from -1 to 2 minus the same antiderivative, 4x minus 1/3 x cubed, from 2 to 3.
Why are you subtracting?
Because the integral, since my function is below the x-axis, is going to give me a negative answer. Right? I don't want a negative answer for this. I want a positive answer for this.
Oh, so like the negative sense.
Right. You could put plus the absolute value of the integral. You could do that also. Okay? So then let's see. This is going to be 8 minus 8/3 minus -4 plus 1/3 minus, let's see, 12 minus 9 minus 8 minus 8/3. There's a lot of negatives and stuff to keep track of here. Let's do a little distributing. So 8 minus 8/3 plus 4 minus 1/3 minus, I'm going to go ahead and do this. The 12 minus 9, that's 3. That's pretty easy. It's going to be minus a -8, so that's going to be plus 8. And minus a negative 8/3, that's going to be minus 8/3. Right? There's a minus, minus, minus. So again, I do the whole numbers first. So let's see, that's 16 plus 4 is 20, minus 3 is 17. Minus 8/3 minus 8/3 is 16/3. So it's 17 minus 5 1/3 is 11 2/3. Oh, did I leave that one off? Well, crud. So this is going to be 17/3. So this would be 5 2/3. So this is 11 1/3. Thank you. So that's going to be 5 2/3. Questions about that? Notice, if we could somehow do the absolute value of this function, my graph would look like this, and I could just do the integral, right? We're going to take advantage of that idea on this next one. Find the area between the curve y equals x cosine 2x and the x-axis over this interval, and you're allowed to use a calculator. So rather than find all the places where this goes below the axis and doing those as negative so that they become positive, the easier thing to do on your calculator is simply do the integral from -2 to 4 of the absolute value of x times the cosine of 2x dx. That way, my integrand is never negative. This graph is never below the x-axis because I'm taking the absolute value. So grab our calculator, do math 9. It's from -2 to 4. Again, I find the absolute value by doing second 0, which gets me to the catalog, and absolute value is the very first thing there. So it's the absolute value of x cosine of 2x. I'm taking the derivative with respect to x. And about 3 days from now, it'll churn out the answer. Oh, there it is. 6.332. All right. Y'all have a great day.